Hello, my name is Matthias and I'm going to show you the code I made for my fifth hand-in. This fifth hand-in we had to make 5 kinds of sorts, which I'm going to show you. We had to make these sorts into, let's say, sort packages. So we actually have a main code, a source code called SortPackage.cpp, and a SortPackage.h, which is the header where we declare our functions to use. And in our source code we're going to make the functions, but not all of them actually, but we're going to go into details with that. And the main function is going to call the functions and going to make the array and stuff, but we'll also get into that. Here we see the 5 declarations of our functions: binary sort, bubble sort, selection sort, insertion sort, and quick sort. And in between we have a print array, which simply just is a function in order to print out the array we're going to make. And let's just go through what they are, just explaining them. Let's first start with bubble sort. In short words, bubble sort compares two elements in an array. Let's say these two, and then take if the first one is less than the second one, they swap. Or if it's higher and less, then it swaps. So we want to have all the lowest one in this end and all the highest one in this end. And then we proceed like, is 6 bigger than 4? Yes it is, so they swap. And then this is 6 and 7, is 6 bigger than 7? No it isn't, so they don't swap. And just proceed like this and all the way to the end, so the highest number will end at the end. And then we go back again until the second highest number will end at the second end, and then again and again. That's simply the bubble sort. The next sort is the selection sort. What the selection sort does is that it runs through the whole array, trying to find the lowest value, which is in this case 0, and put it on the 0 position of the array, and then proceed starting from the first position of the array and going through the array, finding the lowest number, which is in this case 1, and put it on position 1 over here. And that's basically selection sort. And of course, whenever I swap a element, I of course swap it with the one being in that element. So 5 is going to swap with 0. Next we have the insertion sort. And what the insertion sort does is that first of all it takes first one element to see if this is smaller than the next one. Then of course it only makes sense if you take 2 elements, see if 6 is smaller than 5, and then swap these. Then when this is in position and when this is sorted by this part of the array, it takes another element and then says, is 4 smaller than 6? Yes, it swaps. Is 4 smaller than 5? Yes, it swaps. And then this array part is sorted. And then we take a next element, and so on and so forth until we have a sorted array. And that's basically also what an insertion sort is. Now it becomes more trickier with binary tree sort and quick sort. Let's first take binary tree sort. And what binary tree sort does, it takes the first element of the array, and then we take the next one and see if it's bigger than smaller, then puts it down here, if it's smaller to the left or if it's bigger to the right. And then we proceed, and then if it becomes a number which is then again smaller, it's going down. Let's say this is 2, then we have a number 1 which is smaller, it goes down here, and here we have number 1, the number of 0, so 1 is bigger than 0, and it's going to jump to the right. So it's going to jump to the right down here until we've sorted the whole array going from smallest to biggest here. And that's basically a binary tree. And then quick sort, which is a quick sort partition sort, which works like this. If we start by taking a pivot from the array and then putting the smaller numbers of the pivot to the right side of the pivot, and the bigger ones to the right and the smaller ones to the left. And then we simply take these partitions, which is a part for itself, because now we know the pivot is in its right position. We're going to take the new position, find a new pivot point, let's say this pivot point, and then put it, order it so that the smaller numbers than this pivot point is going to be to its left and the bigger ones to the right. And that's basically it. We just proceed recursively doing in this function until we've sorted the whole sorted list. Inside our source code and our main code, we have to include the SortPackage so it counts for both the main code and the SortPackage code, which we call the included directive. And yeah, and let's just first take a look at bubble sort, which yeah, and then take the easiest one first, and then go to the more difficult ones. As you see here, we have the bubble sort void function, and if we are inside the SortPackage, we have the functions. And we use a for loop going from 0 to 10, since that's our size of array. And what we, actually we should just write size array. I haven't done that because I know my size of the array is 10. So I just go like this, and then I say make a for loop, and inside the first for loop is the index of each of the elements inside the array. So first we take the first one, and actually you can say this is like the first for each number you're gonna put into place. So this is gonna count the first number ending at the end. And then for the inside this, for the first element to find the highest element, we're gonna have this function, run function, for loop function inside it, which runs until the number is at its end, or the biggest number is found. And then of course we have to minus with 1 for this loop each time, so we only run 9 times after run the first time, since, oh sorry, 8 times because we only run 9 times. But we have to minus it because we don't want to run too many times, because when we only have like 5 numbers left, then we need to only do it 4 times, since we already have something in place. And then we actually just do the swapping down here, which we state that of course this is only going to swap if the number next number is smaller than the number before. Yeah, like if 4 is less than 6, we're going to swap. And then swapping is done like this, where we temporarily store data from the RAT, and then so we can put it to something else, and so we can put RAT to be, yeah, let's say this temporary, we have temporary here, we store 4 inside here, and then assign the position here to be the same as the position here 6, so both is actually 6 here, and then assign 6 the position of 6, which is t where we are at the moment, minus 1. We assign the number which we have in the temporary. So this is going to be 4 and this is going to be 6. It's pretty basic. The selection sort and the insertion sort is quite the same. Just in the selection sort, we first find the lowest number inside the array, and then afterwards we're swapping it down here. And just instead of swapping these two as we did before, we're going to swap the minimum, which is the start position of the index over here. We're going to swap that with the minimum number find, which in this case is going to be this one. And yeah, and that's basically it, I guess. That's not so different from the other one, except you're going to find the number before you swap instead of swapping all the time. And insertion sort is somewhat the same, but you just use a while loop instead, saying that of course j have to be bigger than 0 in order to have it to compare it to something. If it's 0, then it's just this position. That's not very efficient or effective. So we just say let's just say the part is here, and let's say while this 4 is less than the coming numbers down here, or just, yeah, it's gonna swap, and then j is gonna be minus by 1, since we want to check the rest of the array. So if this is true, then it's gonna swap, and then j is gonna be minus 1. So instead of checking for these two, it's gonna check for these two instead, which is 4 and 5. And yeah, that's also pretty basic. Let's go to the hard stuff. Binary trees. For binary trees, we use 2 structs, which is pretty atypical in a head file because I have inside my struct I have a function, but it works and it's pretty decent. First off, we have a node which we call tree node, which include a struct which includes the data inside these nodes in the tree, and the pointers saying the legs of the tree, left and right. And what we then do is we have a new struct which includes a function, meaning build function. It's going to build it, of course, which include a pointer and then the integer value of inside the node. So what it does is that if the value is smaller than pos data, meaning that the first point, of course we should also include that we're gonna inside main function have declared the first one, the first node in the binary tree called the root, which is, where is it? It's hiding somewhere. Oh, sorry, it's not here. It's inside of here. Binary tree, which is stated down here. So the first one is we're gonna create a new node called root, the first top here, and then we're gonna assign the feet to null, both of them, not pointing to anything, and then meaning that the root is gonna be the first element in the array. And then of course when we have to call this function, we need to use the struct and make an instance of it, and then in order to build it, we need to build it for as big as the array is, and then we need to print it out, of course. And all of this is just inside the binary tree sort function, which is gonna be, we're gonna use now main function. So that's just for, and that was just the part. So the first part was just to make the root. So let's go into the head package again. So we have the root, and it says if we then have the position left is equal to null, meaning there's nothing in there's nothing in the pointer isn't pointing at anything except 0. Then we can make a new node, and we're gonna put in the value of the new node. We're gonna make some legs in that node. But else, if there are something, we're gonna actually run the function again, but not from the tree node pos. We're gonna run it from the pos left, meaning we're gonna run from this node. Okay, and then we're gonna still have the same value in the function, which is it's the array, a element in the array. And then we're gonna run it again and see if this has any more elements. And if it, of course, is an element here, it's gonna run again, and then this element. It's just gonna keep on going until it finds something that's pointing at null. And then if else, if it's not less than if it's not equal to null, but the value is not less, so it's not going to the left, it's just going to go to the right and do the exact same, just at the right foot, meaning on this side. And that is pretty much what binary tree set does. And then in order to print it out, we go inside this function where we are going to have void print tree, and what it does is that it's going to go from the leftist side over here, and it's going to find it. So if it is not equal, if we start at root again, if left foot is not pointing at null, it's going to run the function again, but just from this position. So it will go automatically all the way to the left part of the binary tree until it reaches null by recursive functions, and then it's going to print out when it then gets to null. It's going to print out the data, and I do not have any more time, so I'm just going to have a short break.